This is the National Tropical Weather Conference live channel. It is made possible by USAA, the South Padre Island Convention and Tourist Bureau, and Plilox Hurricane Clips. NTWC Live is a team effort. We have Tim Smith and Bill Reed that help us out with this. This morning, Tim is busy in the Rio Grande Valley working a hurricane event. We have Bill Reed with us right now. Bill?
Thanks, Alex, and good morning, everybody. A lot quieter in the tropics this week than what we were looking at over the last couple of weeks. Looks more typical of June. There's a non-tropical low off the East Coast that'll move inland in the Carolinas and produce quite a bit of rain there, but not expected to develop any in the tropical sense. And later this week into the weekend, there's only a low chance of a development in the Eastern Pacific, way away from land and moving westward. Nothing in the other basins that we know of in the next 5 days. This morning we have a return appearance from Sean Sublette, who is a meteorologist with Climate Central and leads the production of the organization's Climate Matters program. Prior to this, he was an on-air meteorologist with WSLS in Lynchburg, Virginia, and was also an adjunct professor at Lynchburg College. Sean earned the Master's and Bachelor's of Science in Meteorology from Penn State University. So welcome back, Sean. Take it from there.
Bill, thank you very much. Alex, thank you for the invitation as well. And hello, everyone. I'm in suburban Philadelphia. Our office is typically in Princeton, New Jersey. Our organization, for those not familiar with it, is a nonprofit science, communications, and journalism organization. And basically, we're created to help be a good media liaison to this, from the scientific community to the public, about climate change, its impacts on people, more than just so much polar bears and the like. So with that, I'm going to take an opportunity to share my screen. And bring it up full. All right, so there's my intro slide. I'm assuming everything looks good and sounds okay, so we will press on. Basically, what I want to talk about is impacts of climate change, and then really kind of walk into the tropical aspect of that. So let's step back just a little bit. What we're looking at is Houston, shortly after Harvey, and the phenomenal flooding that took place as a result. That lasted for a very long time. The important thing here is that climate change isn't just one of these polar bear things. There are a few takeaways from this, bullet points, if you will, to think about long after this is gone. First of all, climate change is already happening, and it is by and large human caused. Some impacts are irreversible, but the actions we take today, tomorrow, in the coming years to decades will in fact limit how much warming goes on in the numerous decades to come. So what does climate change mean for us as people? Well, first of all, we have to start thinking about extreme heat, especially in urban populations and urban centers where the urban heat island exacerbates the problem. You're going to have more incidents of heat-related illnesses, such as heat stroke, heat exhaustion, and the like. In the Western US in particular, it's going to enhance wildfire activity. Important to realize that climate change doesn't cause wildfires, but because it tends to dry out vegetation more rapidly, it does enhance the spread and intensity of wildfires. Same thing with drought. I mean, climate change doesn't force drought, but because you have a warmer environment, which means there's more evaporation, that means your droughts are going to be exacerbated. And in turn, that's going to affect farmers and ultimately food prices as well. And then for those along the coast, since we're at a hurricane conference, even away from specific tropical or extratropical cyclones, we're seeing incidences of coastal flooding on the rise, even just away from storms, these regular high tides, or sometimes they're called high astronomical tides, king tides, with the ocean water warmer, and lots of land ice melting and starting to run into the global ocean. Those two things acting in concert do bring the sea levels up. So all else being equal, with the higher sea level, when there are abnormally high tides, even those that are just astronomically driven, they are going to progress farther inland and thus cause more damage to infrastructure. And of course, just heavier rain. And with heavier rain, we're talking about these specific heaviest events, not so much, oh, well, we had a quarter inch of rain, or maybe we had a half an inch of rain here or there. But these incidences where we have very heavy rain, it tends to be even heavier. So the very short version is climate change takes a bad situation and largely makes it worse. Want to be careful not to suggest that climate change is the root cause for every single bad weather phenomenon that's ever happened, because it's not, but it does make things that we're already vulnerable against even worse. A little background for those not as familiar with the science, and this reminder that the atmosphere contains mostly nitrogen and oxygen. When I taught at University of Lynchburg, what was in Lynchburg College, I was just shocked how many of my undergrads did not understand that concept. But of course, there are very important trace greenhouse gases. Water vapor, carbon dioxide are the two most important. Methane and nitrous oxides also important, but when we think about how much gas is out there and doing the work, if you will, of warming the planet, we think about water vapor and carbon dioxide. The other thing that I think needs to be reminded to a lot of folks is that the sun doesn't heat the atmosphere that much all by itself. I mean, the sun heats the ground, and then the ground heats the air above it. All right, and then depending on what kind of gases you have in your atmosphere, in the air above the atmosphere, that goes a long way in determining how strong your greenhouse effect is going to be. And all the calculations have shown, and I remember this as a first year undergrad, just beating into my head, that without the atmosphere, Earth would be about 60 degrees Fahrenheit colder than it is today. So some greenhouse effect is vital for life on Earth. But as they say, too much of a good thing is not necessarily a good thing. All right. The science of this is well known and very well established. It goes back to the middle and latter part of the 19th century. John Tyndall, Sabine Arrhenius, all did very early calculations long before there was any such thing as a computer, much less a computer model, determining that if we had an increase in carbon dioxide, we're going to have an increase in surface temperatures. And we know that the climate can change because it has changed in the past naturally. And there are mechanisms, sometimes you'll hear these called Milankovitch forcings or Milankovitch mechanisms, or basically orbital mechanics that have changed the distribution of solar energy into the planet, basically where it's coming in and how long it's coming in. The Earth's orbit is not a perfect circle. It goes in this kind of 100,000 year cycle where it's a little more elliptical than others. It's often known as precession of the equinoxes, axial precession, or the wobble. The Earth's axis is kind of like a spinning top, and it goes through this 26,000 year cycle where the axis is pointing in a different direction in space. Plus, the third of these forcings is the change in tilt of the Earth's axis. I was brought up, it's 23.5 degrees as a kid, but it actually varies. There's a 41,000 year cycle where it goes back between about 22 degrees and 24.5 degrees. So when you look at these three things in concert over very longer term, multi-thousand to tens of dozens of thousands of years, that's how we know climate changes naturally, away from any kind of human mechanisms. So how can we go back and determine what the climate was in the past, since we don't have great thermometers before the 18th century? We need to go back and use paleo records or paleoclimatological records. These are things like ice cores, tree rings, corals, sediment cores. We can go back in time and see the chemistry of these things, and they will tell us a lot about what the climate was during much distant times in the past. Not what the temperature was on any particular day, but what the long-term climate was like years to decades at a time. Ice cores, for example, these are basically, you take a big drill, you go to Greenland, you go to Antarctica, and you drill down into the ice core, because each year there's a teeny tiny bit of melting, and there's some snow, and there's a teeny tiny bit of melting the next year, and then there's some snow, and that actually traps little bits of ancient air from the atmosphere during that time. You can take that into a lab in Colorado, run that into a vacuum chamber, and very precisely tell what the constituency of the atmosphere was at that time. Ring patterns in trees will tell you tree stress, which will tell you something about drought. And then coral shells, you look at the banding structures in those, they can tell you something about temperature. And the sediment cores, along lakes, rivers, oceans, they can tell you about the chemistry, which in turn tells you about the amount of carbon dioxide that was in the atmosphere. So these are ways we can go back and say, well, how do we know what the climate was like 6,000, 8,000, 10,000 years ago? These are the ways that we do that. So when we go back through some of the strongest ice cores, or the best reliable physical evidence, easily show that the current concentration of carbon dioxide in the atmosphere, which is about 417 parts per million, is higher today easily within the last 800,000 years. And there have been some computer simulations or modeling studies that suggest that the level today is higher than in the last 2 million years. So this is easily the highest amount of carbon dioxide we've had in the atmosphere since basically the advent of human civilization. So let's go back to when we had the last ice age. We came out of that about 20,000 years ago. And then there was this very rapid warming where we got close to the climate, if you will, that we're kind of familiar with now over these last 8,000 or 9,000 years. That's when agriculture starts to emerge. That's when we actually start forming societies as humans. And certainly, there have been these fluctuations. You've heard of the medieval warm period, how it was also a little bit warmer in Greenland than it was today, but it's certainly not as warm from a global aspect as what we're seeing out there today. And that bar you see on the right side of the graphic gives you this large uncertainty of how much more warming could happen as we go forward in the next several decades to century or so. And it's such a large uncertainty because we don't know how much more carbon we're going to put into the atmosphere here in the next several years to several decades. And that's going to tell us a lot about how much warming to expect, especially as we get into the second half of this century and beyond. When we do look at the stronger temperature records that using actual thermometers, which goes back to the late 19th century, and we look at the concentration of carbon dioxide, we see that it is not a perfect match, but the trends here match very well. There are certainly some fluctuations here or there. Maybe there was a volcano that went up. Maybe we had a little more economic prosperity, which may have put a little more soot or something like that into the atmosphere. So it is not a perfect one-to-one correlation, but you see the trends match very, very well. And the other thing to think about here, especially the last 50 years, obviously the sun is a very dominant feature in our climate. And when you look at the global average temperature here, again, going back to 1880, and this is from NASA, so it's in Celsius there on the right. The temperature is your red curve, and then the solar output is in the yellow curve below that. And you can see up till about 1960 or so, those things are going along pretty well. But then as we got into the 70s, and then especially beyond that, the global average temperature continues to drop, even though the solar activity has flattened or arguably even come down a little bit. In fact, NASA did another study and had a little release on this earlier on this year, where they mentioned that the warming from greenhouse gas emissions is 6 times greater than any possible cooling that could be coming from a grand solar minimum. We've heard that term kind of tossed around a lot. And again, the sun's important, don't misunderstand me, but we've put enough greenhouse gases in the atmosphere from burning fossil fuels to far outweigh any kind of grand solar minimum or decrease in solar irradiance or solar activity. So let's talk a little bit about these computer simulations, all right? And a lot of squiggly lines here, so let's step back a little bit. We want to know how good these global climate models, these simulations are, all right? So we take the conditions as they were at the end of the 19th century, all right? We feed them into the computer models, computer simulations, and then we run them forward in time. It's like, well, what kind of result do we get after about 100 years? All right, so the red curve there, the red trend line there, are the observations. This is what we have actually seen. So obviously there's a big temperature, and you see that jump, just like in the previous graphic, as we get past the 1960s and into 70s. So the red line is the observation. When we include all the forcings in our climate models that we know, both natural, including solar, volcanic, and what we're putting into the atmosphere regarding greenhouse gases, what those are called anthropogenic or man-made, when we incorporate those into the model, that's the green line, and that matches pretty well with what we see with the observations. When we go back to the beginning of that simulation, and then we remove the anthropogenic or man-made forcing, basically the additional greenhouse gases, but leave everything else in, we get the blue curve or the blue trend line, which is significantly cooler than both what's observed and what we've simulated. And that's eerily similar to the previous graphic where we showed how even though the solar activity has come down, the temperature continues to climb. So there's good observational evidence, and we've got a reasonably good handle on the global picture regarding temperature. Obviously, any individual spot on the globe is going to be a little bit different, but when we're looking at the big picture here and try to understand it and try to get a handle on what's going on globally first, we've got a pretty good handle on it. You know, carbon dioxide gets talked about a lot, and this is why. This is the fuss over carbon dioxide. When we look at the greenhouse gas emissions, and this is specifically from the United States, you know, 82% of it is carbon dioxide. There is methane going up, and there's NO2 and fluorinated gases, but the lion's share of the work here is carbon dioxide. And the reason why we're so concerned about that is that it stays in the atmosphere for a very, very long time. Methane naturally settles out of the atmosphere much more quickly, nitrous oxide to a secondary extent. But there's no natural rapid way to remove carbon dioxide out of the atmosphere. It does happen on those geological timescales. When I showed you those graphics of the turning Earth and the Milankovitch mechanisms, but it's 1,000 years. You know, these are long rocks weathering geological processes that take carbon dioxide out of the atmosphere. So once it goes up, for our intents and purposes here, carbon dioxide stays, and it's going to continue to warm things up for decades to centuries to come. So where is it coming from? Most of it is in our generation of electricity and transportation, you know, basically driving to work, driving to school, driving to the grocery store, wherever. So that's where more than 50% of the greenhouse gas emissions domestically are coming. Certainly there's some in agriculture, some commercial and industry, but most of it is transportation and electricity. And there is widespread consensus on this. You know, we do live in a very, let's say, interesting time when it comes to information getting out. But there is large dominant consensus that this big picture is happening. I mean, we can have little discussions here or there as to how much this might be affecting tropical cyclones, how much could this might be affecting atmospheric circulation. But in terms of whether this is happening at all, there's a dominant consensus that it is happening, no question. So when we look at what are the 10 hottest years on record globally, again, this is back to 1880, the last 5 years in the global record have been the 5 hottest. 2016 was the hottest on record, 2019 a close second. Reason 16 was a little bit hotter, I think most people would agree, as we were coming out of a very strong El Nino, the warming of the Pacific, equatorial Pacific Ocean. So far in 2020, we're on par with what you see there in 15, 19, and 16. So it's very, very likely we're going to be top five, maybe even number two or number three, judging on how we've come so far in 2020. Now, there are multiple laboratories, if you will, that are doing this global temperature average. And one of the things we like about science is that when you do a good experiment, it's repeatable. Different labs doing the calculations slightly different ways in terms of what's a global temperature average, because you have to make some assumptions. You can't have a perfect result because you can't perfectly simulate the atmosphere. You can't get data points from every single part of the atmosphere. So anywhere from the Met Office in the UK, NOAA, NASA, the folks at Cal Berkeley, Japanese Meteorological Agency, they've been doing these calculations or running these calculations forward from about 1880. And again, you see a few different notes, but the song is still the same. There is widespread scientific conclusions or consensus that the planet is warming, and we are largely to blame. When we look at the United States in particular, again, you see the bars there, 1900s, teens, 20s, 30s were hot. No question the 1930s were hot. But when you look at the United States as a whole, you see that bigger jump taking shape 80s, 90s, the aughts, and the 2010s. You know, the average temperature for the decade has come up about 2 degrees Fahrenheit in the last 50 years. That's only expected to rise even further. So when we think about the average temperature, what does that mean? Well, you know, if the average temperature is only up a couple degrees, well, what does that mean? If you think back to school and you would hopefully get your grades on a curve, that's what this kind of bell-shaped distribution is saying. You know, let's take a day, let's say today is the 16th of June, and for 100 years, you're looking at what the temperature is every day in your backyard on the 16th of June. Some days you get very hot, some days it's kind of cool for the time of year. But most of the time you're 70s or 80s, maybe close to 90 in a hotter climate on average. But as that whole average shifts to the right there, you're going to have an increase in this extreme heat. These temperatures that might have only happened once every 10 or 20 years might start happening every 5 to 10 years or every 4 to 8 years. All right. And these cold temperatures for that time of the year, again, that used to happen once every 20 or 30 years might only happen once every 50 or 60 years. All right. So it's not like cold just goes away forever. In the colder climates, it doesn't mean it's never going to snow again. That's just balderdash. All right. But what we're seeing is that when heat does occur, it tends to occur more frequently and it tends to become more intense. The cold still happens, but it is less intense and it tends to happen less frequently. So we can look at the number of record highs versus record lows back to the 1920s. That's where our better records are here regarding record highs versus record lows. So for this graphic, per decade, we're looking at the daily record highs versus daily record lows at all sites across the United States as a percentage. So basically, if there was a record high, we put it in a column. If there's a record low, we put it in a column. So what we see here in these last 3 decades in particular is that the number of record highs is continuing to outpace record lows. And if you think about it intuitively, the longer your period of record, the harder it is going to be to break a record because you've got more data to work from. All right. So again, the second group there from the left is the 1930s, unquestionably a hot time. But now we're starting to see areas that are hotter than that. And the trend on that has really started to be borne out 70s, 80s, 90s, and into the aughts, into the teens. All right. So the data is largely there. Let's start pivoting a little bit toward oceans, and that leads us into tropical cyclones and hurricanes. One of the things that surprised me, or I didn't think about it intuitively as a meteorologist studying the atmosphere for 20 years initially, is that the energy from greenhouse warming largely is going into heating the ocean. 93% of that additional energy is actually going into the ocean. All right. And we know that it takes a lot more energy to raise the temperature of water than it does to raise the temperature of air. So with that in mind, you have to start thinking about, okay, well, what does this do to oceans? What does this do to circulation? What does this mean when your ocean is warmer and you start to put more moisture back into the atmosphere from a warming ocean and a warming atmosphere? That's going to ultimately affect how storms did this earlier, is the sea level rise. You've got the warming water, warm things expand, plus you've got melting. Sea level rise over the last 100 years is unprecedented at any time over the last 2,000 years. So obviously there's little fluctuations, always some natural fluctuations and some natural variability. But what we're seeing now is starting to move away from that natural variability. So another way to kind of step back and think about this a little bit for those who are familiar with thermodynamics, or if you think about as a kid, you learned about the water cycle, evaporation, condensation, precipitation. Some of you even learned a song about it. That's the way my kids learned about it. But the water cycle is basically ramped up. You're putting more energy into the water cycle because you're providing more energy into the earth as a system as a whole. So you're ratcheting up evaporation, you're ratcheting up condensation, and you're ratcheting up precipitation. All right. The earth is more than 70% covered by water. So it's really, really easy to supercharge the water cycle here. For about approximately every 1 degree increase in temperature, you can get about 4% more water vapor into the atmosphere. And that's ballpark. It's not precise because you have all these, again, minor localized fluctuations. So turning this back to tropical cycle, have warm sea levels, does not mean we can go on coast, that the storms are slowing down a little bit. That's not widespread, but there's some evidence of that. And again, the storm surge is pretty basic and pretty straightforward. When we go back and look at the heaviest precipitation, all right, and I alluded to this earlier, in those heaviest precipitation events, the amount of water is coming down is greater. For example, let's say in these charts, we looked at the 100 heaviest rainfall events, if you will, in each parts of the country. And this is from the National Climate Assessment. The heaviest 1% of these events is getting heavier. All right, so there's about 55% more rain in the heaviest rainfall events in the Northeast. There's about 27% more rainfall coming down in this 1% of heaviest rainfall events in the Southeast, 42% in the Midwest and the Great Lakes. And, if you follow meteorology enough, you know that once you go to the Western Plains, Front Range, and off to the West Coast, that's a much more arid climate in general. So that kind of makes sense that those figures are a little bit lower. So this place that is in a relatively humid climate, you are going to have more precipitation. This is the general amount of warming that's taken place in the global ocean since about 1901. And this one is in degrees Fahrenheit. So you see a large part of the global ocean has warmed about 1 to 3 degrees. Unquestionably exceptions. And the other thing arguing into the previous cooler phase of the AMO back into the 70s and 1980s. Rapid intensification has gotten a lot of headlines the last 2 or 3 years. For those not familiar with the term, when a storm undergoes rapid intensification, that means that the maximum sustained wind speed, not the gust, but the sustained wind speed increased 35 miles an hour in 24 hours. All right, and for the storms that do become major tropical cyclones / hurricanes, about 4 out of 5 of those will go through that process at some point. Most of the simulations do project this to happen more in a warming world. All right, we've seen a little of that, but I think the jury, to be frank, is still kind of out on that. When we look at just the intensifying Atlantic tropical cyclones, the rapidly intensifying Atlantic tropical cyclones, hurricanes, you don't see a big trend. I ran a straight linear regression on this, and it suggests a change from 3.5 to 4 over the past 70 years. And I think that might be a little hand wavy, if you will. But, we need to be very mindful of this going forward. as that if you are in a condition where the water is warmer, that is one more ingredient that is going to favor rapid intensification. You've got to think about other things like shear and wind direction with height close to the coastline as well. So there's a lot going on here. But in terms of strictly Atlantic systems, we see perhaps a little bit more, but again, I think the jury's still out on that one. I do want to quickly address this paper that came out 2 or 3 weeks ago by Jim Cosin up in Wisconsin, when he was looking at reviewed global tropical cyclones, kind of increased their period of record in the satellite era from 1979 to 2017. And he and his group there looked at the proportion of major hurricanes compared to all hurricanes. In other words, how many more hurricanes reach major category, that 3, 4, or 5, compared to all hurricanes as a total. And there's the proportion on the left, it goes from about 30 to almost 40%. And each one of those dots is a three-year summation, a 3-year average. So we see a little bit of an increase in this thing. And so I think evidence is starting to gel around the idea that hurricanes may be getting stronger, but in terms of the number, that's still way out there. Back to the rain itself, and this is for not just tropical cyclones, this is for all rainfall. And here we're looking at the number of calendar days where there's more than 3 inches of rain at all sites across the United States. So in an average year, that's the 100% line, all right? So since 1950, we've seen the amount of precipitation, number of days with 3 inches of rain on the way up. Again, ups and downs through time, to be sure, natural variations, year-to-year fluctuations. But now what we're starting to see in this warmer atmosphere where there's more water vapor in it and you can produce more precipitation, the heaviest rainfall is starting to trend heavier in all locations across the country. Now, the other thing that makes a lot of headlines is when we do have a bad hurricane, did climate change cause this? And again, that I'm just not a fan of that question to begin with, because hurricanes have always been around. So this one was from the World Weather Attribution Project. They're actually based in Europe. And they quantify this the best they can, that the rainfall in Harvey was about 15% more intense. And the odds of something like Harvey happening, or the main amount of rainfall with Harvey happening, about 3 times more likely in a warming atmosphere. All right, so this is more of a statistical analysis. You might sometimes hear it called weighing the dice, or maybe you've put an extra ace or 2 in the deck of 52 cards to kind of weight the odds towards something happening. So as I alluded to before, we've always been vulnerable to bad weather, if you will. But the climate change impacts basically take things that were already vulnerable and make them worse. Some analogies to kind of think about the difference between weather and climate, because you're still going to get, a couple of years ago, we said that brutal Arctic outbreak in the Midwest near the Great Lakes. Those things will still happen, all right? Weather is like a boxer throwing punches. There are going to be some strong punches that hit. There are going to be a few swings and misses, all right? But in terms of what's governing the boxer, climate has to train the boxer. Climate is telling how the weather should operate. So if we're changing the climate, ultimately we're going to start changing how the weather operates in a particular climate. I'm a Penn State guy, so we'll pull this one up as well. Weather is one football play. Your guy might break for a touchdown. Your quarterback might get sacked. You might have a great incomplete pass. You might have an interception. All right. But climate is the whole season. How did it play at the end? So you could use a baseball analogy here as well. Climate being like one pitch or one inning or one game. Climate's the entire season. Even the best pitchers in the major leagues gave up home runs. Going back to the football analogy, Tom Brady, love him or hate him, he still threw interceptions, even though he's won all those Super Bowls. So again, weather is very, very short term. You can't talk a whole lot about one day's weather in the course of climate. You've got to sum it all up. Now, regarding public opinion, we have seen a change here. This is from our colleagues at the George Mason University Center for Climate Change Communication and the Yale program on climate change communication. They've been keeping the pulse of American attitudes toward climate change since about 2009. And, too often times we fall into this yes or no, heads or tails, plus or minus thing. And it's a lot more nuanced than that. When we look at these bubbles in the top row, from left to right, you're looking at basically the percentage of people who kind of fall into this category. Ones to the left are most alarmed about climate change, ones to the far right, in this case, just think it's all a bunch of hooey. So what we've seen over the course of about the last 9 to 10 years is that more people are becoming concerned or alarmed about climate change. You're always going to have a core number of people who just don't think it's going to happen. And frankly, you probably will never reach them. But what we're seeing is a fundamental shift in the dynamic toward people accepting the fundamental science of climate change. We can argue about the small scale effects here or there. The other thing I thought was very interesting about this is the number of disengaged or ones that really aren't paying attention has dropped substantially. And some have wandered over into the right-hand side, but most people who had been disengaged are kind of going over to the left part of the column and becoming a little bit more accepting of the science. So thinking ahead a little bit, what we do now, next year, decade, couple of decades, will go a long way in determining how much warming happens. We're already probably about 1.5 degrees Fahrenheit warmer to 2 degrees warmer than we were 120, 130 years ago. And the warming is going to continue. We have to decide how much more, warming is going to happen by determining how we're going to use energy. My colleague at Colorado State says, the best thing we can do to generate energy is stop setting carbon on fire. Because, you burn carbon, you get carbon dioxide, goes in the atmosphere and stays. And there's no really good way to get that out. So these are kind of a couple of the take-home points, if you will. Carbon dioxide does go in the atmosphere and it stays for hundreds to thousands of years. All right. And that does ultimately lock us into additional impacts on people, rising sea levels, more extreme heat, and heavier rainfall. I've heard the argument, well, who's to say what the right temperature is for everybody? That's fine. But even if you somehow acclimate to that, you've got a massive amount of people living near the coast that are probably going to have to start to relocate. It's not like it all sneaks up on you one day and you're flooded out. It kind of comes up over time, over the seasons to years to decades. The tides just keep coming higher and higher and higher. And then ultimately, you end up with a situation where you just don't want to live there anymore. And what I expect is going to happen is that property values will drop first, and then people will ultimately start evacuating or leaving or relocating, what have you. So that's the core of the presentation. Some additional places to go to, because we always encourage people to do your own research, as they say, but please don't do yourself a disservice and wander down the rabbit hole. Find some very strong places to look. NASA, quite frankly, is my favorite one. They have some excellent resources there, excellent visualizations. You go to climate.nasa.gov. The U.S. federal government's National Climate Assessment. These were things that were mandated by Congress back in the Bush administration, the first Bush administration, I believe. There are two parts of that. Basically the physical evidence at science2017.globalchange.gov, and then the second half of the National Climate Assessment came out in the fall of 2018, and that looks more specifically at what you might be able to expect at different regions of the country, because obviously things in Montana are different than Florida. So that second one there, NCA 2018.globalchange.gov, gives you more of a regional aspect. And of course, got to put a plug in for my office, climatecentral.org, and a lot of the graphics you saw that were put together by our office. and they're all available publicly at medialibrary.climatecentral.org. And if you want to go back and look at some of that paleo stuff I mentioned, the ice cores, the sediment rings, all the corals, all that, you can just Google this from PBS Nova. It's called Decoding the Weather Machine. It's about 2 hours. Pour yourself a cup of coffee or whatever, and sit back one morning and watch that. And because it shows you the scientists that are doing the hard work, going to some remote locations, doing literally the digging and doing the analysis to find out what the climate used to be like many years ago. A little plug for my particular part of the office. Our program is called Climate Matters at Climate Central. We do send out a newsletter every week that is focused toward climate news in one particular part of the country. And you can sign up very easily. It only goes out once a week. We don't want to clutter up anybody's inbox, but we try to keep the pulse of what's going on. We like to do local data analyses wherever possible, and we also will highlight some bigger climate news as well. Design that was put together by Ed Hawkins in the UK a few years ago. So that's a quick overview of my stuff. I'm going to stop sharing the screen so we can say hi to everybody once again. And Bill, if you're there and if anybody has any questions, I'm happy to answer them.
Sure. Got a few that I've noticed here. Here's an interesting one that you probably have the answer for. How do we account for changes in observational density when assessing the increase in extreme rain events?
That is a good one. That one is a little bit beyond my purview. Some of the best people doing that, Ken Kunkel at NOAA. He'd be a very good person to talk to about that. He's one of the people we lean on a lot for our analysis and determining, well, exactly your point. The observational network is a lot different than it was 50, 60, 70 years ago. So there has to be some, I hate to use the words nudging, but you've got to look at your data. You've got to look at the quality of your data. You've got to recognize where data is bad and needs to be thrown out. And that is a kind of a subjective process, but we try to make it objective as possible. So there's a lot to be said for that. So there's no question about that. So I'm not to answer that question, but Ken Kunkel is the first person that comes to mind, and he's at North Carolina State.
Great. Scientists anticipating a change in how El Nino varies as we get warmer in the ocean and atmosphere.
That's a tough one. And the jury's out on that. I've read some stuff that says it's going to be, the El Ninos will be more intense. And I've read some things that says there's going to be higher variability. So I think jury's still out on that as well. But thinking about the big picture here, we do know that the water is going to be warmer in the mean as we go forward. What that means for things, for the wind circulation along the equator, and what that means for shear and hurricanes is still a lot of an open question. And as I said before, there's no expectation that we're suddenly going to have 25 or 30 hurricanes every year. That's just not, I think, anything anyone is expecting. But once conditions do form, the fuel that is available for hurricanes / tropical cyclones will have the tendency to give them more strength.
Great. I'm fascinated with the study that I think Kosin was a co-author on about the observation that over the last several decades we're moving slower at landfall, and there's a large number of 20-inch plus rainfall events here in Texas because we're naturally sitting between the high, blocking high to the west and the high over the Atlantic, and the storms meander in there and lose their steering current. Have you seen anything that shows that type of weather pattern might become more prevalent with climate change? Not yet.
And that is a very active part of research, especially given these last 3 or 4 seasons where we've had these storms. Florence is another one. They come on shore and then they just really slow down and put down these, unconscionable amounts of rainfall. whether that's just the short-term weather pattern or signifying something longer term, that's much, much tougher. And I think, and imagine, Bill, you would agree that, part of the problem is we don't have that many hurricanes to begin with. The variability from year to year in the Atlantic is so high anyway. It's tough. I mean, it's tough. So that's something that continues to be studied and needs to be studied. But right now, I don't think we can say conclusively that that is the case.
Yeah. The other questions kind of related. There's when the attribution studies came out on Harvey, there were a lot of other reputable scientists who were on board with climate change that were skeptical of the precise numbers that were being put out for attribution because of just for an example, how much of the Gulf was much warmer than normal, how much of that a climate change signal, how much of that was a phenomenon that occurred over that particular stretch of the summer.
Right, exactly. That's, that it is subjective. I mean, I know Kerry Emanuel did a study, his group did a study that was a little bit different than the one I showed there. Those figures I showed were kind of means. If you go back in the study, the uncertainties are illustrated. Well, it was probably somewhere between 5 and 25. Unfortunately, for public consumption who are not as familiar, you want to kind of give them one number to work around. So you want to give them something close to the middle. You don't want to oversell it. You don't want to undersell it. You want to put out something that's going to kind of stick with somebody that you think is fairly representative of what the study shows. And yes, that's tricky. So you want to give somebody an idea, but it's not the end all be all. As we said before, different labs are going to make different assumptions, make different guesses, different parameterizations to come up with, all right, this is what we've concluded, and this is why we've done it this way. You've got to look at another lab. Well, we came up with this figure because we did it this way. But I think most of them show that there's at least something. And that's what I said before. Try not to over-focus on the quantification. It is important to keep trying. But the big picture here is that we're going to add this much more on top of it. So that's it. So if you want to throw a 5 or 10% worse thing on there, just as a ballpark, what's in your mind? Harvey would have been horrible in a regular old atmosphere from 100 years ago. It still would have been catastrophic. Lots of Houston, 3 feet of rain, places toward Port Arthur, 5 feet of rain. All right. That doesn't mean that, they only would have had an inch if there was no climate change. That's not true at all. Because as you know, the steering current slowed everything down. And that was largely responsible for the phenomenal volume of rain. All right. But there was this little bit extra put on top of it as a result of climate change, whether it was this much more or this much more or this much more, but there was some amount more.
Yeah, I had one last question on the Facebook feed there. A gentleman was interested in where you could get further information on fingerprints of climate change on extreme events. And I'm guessing the references you showed there, the websites, would probably be the best go-to spot.
The one that we worked with in our shop for a long time was called World Weather Attribution. If you Google World Weather Attribution, you'll see a lot of, and this is largely from the UK and in Europe, and Netherlands. They're the ones that have been doing it the longest. They do it, they look, I think they go back to the 2013 Russian heat wave, I believe, because in terms of figuring out things that are attributable to climate change, heat's probably the easiest one. When you just look at that bell curve that I showed earlier, just statistically, it's harder to get that hot. And if we're getting that hot that much more often, that's a very, very good statistical indication that the overall temperature is going up. And again, I'm not going to sit there.
Well, that was a great talk. I've actually captured a few of your screens there to incorporate in the talks I give relative to heavy rain and hurricanes in the area. It really helped me a lot. Alex, I'm going to turn it back to you in case you have other questions.
All right, thank you there. First, I want to say thanks so much for Sean. Really appreciate that. That was a really great presentation this morning. Thanks for being on the show this morning. Want to remind folks that we still have some more coming up tomorrow. We've got Dr. Joe Cioni, He's going to be talking about some interesting things with drones. We also have other activities that we're going to be having a little bit later, so be ready for that. We've got a lot more programs. We're going to take a week off next week so that we can regroup at 10 a.m.